Chapter 7. String and Time. Section 1. String. Up to now, the data we have processed in the program are numerical values or sequences of numerical values, except for a small amount of text in output function. In fact, the computer can also easily process texts. In the programming language, we call these texts string. String is another data type different from integer and floating point number. In SPL, the text is written directly in a cell. If it can't be identified as other meaningful data type or statement, it will be regarded as a string constant by default. In an expression, we can also use double quotation marks to enclose text to represent a string constant. A1 is the string constant sproc, A2 is a normal calculation cell, and its calculation result is also sproc, which is the same as A1. Similarly, the cell values of B1 and B2 are SPL. A3 starts with a number, but cannot be interpreted as a numeric value, so it is also a string. Like B3, it is 3 plus 5. A4 is a calculation cell that can calculate a numerical value, so it is not a string. If we want to write a string constant starting with equals, we should add a single quotation mark at the beginning of the cell. This extra single quotation mark is not part of the string, and the cell value of A4 is the string equals 3 times 4. Note that only one single quotation mark is needed, do not write another one on the right. If it is written, the single quotation mark on the right will also be regarded as a character of the string. Similarly, A5 is a date constant that can be identified, and it is not a string. If we want to generate such a string, a single quotation mark should also be used at the beginning of the cell, and also, A6 is a legal statement and will not be recognized as a string. To obtain such a string constant, a single quotation mark should also be used at the beginning of the cell. String is also a data type and can be operated. Its most common operation is concatenation, that is, concatenating two strings to form a longer string. Using the plus sign can concatenate two strings such as A2. However, it should be noted that the string part in A3 will be ignored when adding a string and a value. This is a special stipulation of SPL. Most other programming languages do not stipulate like this. Instead, they will either report an error or convert the value into a string and then concatenate. The value can be normally concatenated with other strings by converting it into a string with the string function such as A4. If the slash sign is used to concatenate the string and the value will be automatically converted into a string such as A5. The slash sign can also concatenate two strings directly such as A6. Now, we can use the string to transform the code of prime factorization and display the result as a complete expression. After the execution of this program, a string will be obtained in cell C1, 7215 equals 1 times 3 times 5 times 13 times 37, and the result of prime factorization is written out. If you carefully interpret the execution process of the program, you can imagine how it is concatenated step by step. If there is a concatenation, there is a split. SPL also provides the following functions. The len function returns the number of characters constituting the string, also known as the length of the string. Note that the name of this len function is the same as that of the function getting the sequence length, but the writing method is different. The string should be regarded as a parameter here instead of writing as a1.len. It should also be noted that SPL adopts Unicode, and a Chinese character or a number or an English letter is only one character. In some early programming languages, a Chinese character will be two characters. The left, right and mid functions of A3, A4 and A5 will get apart from the string to form a new string and return. The function name has reflected the part to be taken. Then observe the operation results. It is easy to understand the meaning of its parameters, and we won't elaborate here. Almost all programming languages that can handle strings have these functions, and the naming and parameter rules are the same. A6 split a string into a sequence of characters with a loop function, and you can understand the mid function again. A single character is also a string, that is, a string with a length of 1. The result of prime factorization will always be written with a 1 times in the front. This is because we concatenate a times sign and a factor to the result string every time in the loop. If we don't write the first one, their result will be 7,215 equals times 3 times 5 times 13 times 37, which is wrong. But in any case, this 1 asterisk is a little redundant. What can we do? It can be solved by splitting the string. When concatenating the factor, judge whether the current string ends with equals. If so, it means that it is the first factor. Do not concatenate the times sign, otherwise it will be concatenated. Now we can get the desired result. 7,215 equals 3 times 5 times 13 times 37. We can also do it later and remove the redundant 1 times part. We encounter another function pose here, which will find another string in a string. The former is called a substring. After finding the substring, it will return the position, that is, starting from this position, the character of the original string will be this substring. If it cannot be found, it will return null. This is very similar to the pose function of the sequence, but it also needs to write the string as a parameter rather than the object syntax. We know for sure that there must be a substring equals 1 times in the calculated result string now. After finding its position, we can remove the 1 times part by splitting and concatenating. We can also use the replace function to directly replace replace C1, equals 1 times, equals. Similarly, replace equals 1 times with equals, not 1 times with an empty string. SPL provides many string processing functions, which are not listed here one by one. You can check the help documents when necessary. We just used equals to compare strings. Of course, we can also use exclamation mark equals. Then, other symbols like greater than sign, less than sign meaningful to strings? Yes. In essence, computers can only process numerical values. When processing characters, they should also be represented by numerical values, which is the encoding method. As we said earlier, the encoding method adopted by SPL is called Unicode. Since it is a numeric value, it can be compared with the value. When the strings are compared, it is compared with the character code. The comparison rule is very similar to the sequence, that is, the first character of the two is compared first. If it is different, the bigger one will be bigger. If it is the same, then compare the second character until it is different or one of them is not long enough. In fact, this is the real source of the term dictionary order. So, how do we know which of the two characters is bigger and which is smaller, like strings 1 and 2, or strings 1 and A? Simply put, we can write a code and compare. However, it's too tiresome to memorize all by rote. Let's see if these codes have any rules. SPL provides ask function to return the code of a character. We won't explain it one by one. Please execute these codes to see the results. Here we directly write the coding rules. 1. The coding of strings 0 to 9 is continuous, from 48 to 57. 2. The coding of strings uppercase letter A to uppercase letter Z is continuous, from 65 to 90. 3. The coding of strings lowercase letter a to lowercase letter z is continuous, from 97 to 112. 4. The coding of Chinese characters is relatively complex and no clear rule can be seen. This coding standard was originally called ASCII. And Unicode is extended on the basis of ASCII, so this function is also called ask. In reverse to the ask function, SPL also has a char function that can convert the coding into a character. We can use the char function and the rules just found to write a function, given two integers r and c, calculate the name of the cell in row r and column c in Excel. The main difficulty in calculating the cell name is to calculate the column name. First calculate the number of letters needed, and then calculate the letter string corresponding to the column. Conversely, the ask function can be used to inversely calculate the row number and column number from the cell name RC. The upper function is used to capitalize letters. The rule of Excel cell name looks simple, but it is not easy to come up with the correct calculation logic. As we said earlier, the program code will not help us solve the problem, but will only help us realize the solution. Section 2. Split and concatenate. We have used the loop function and mid to split the string into a sequence of single characters. Because this is very common, SPL provides the split function. S.split is equivalent to len s.mid s tilde 1. Split also has more string splitting capabilities. However, before we talk about split, let's learn a clipboard function. Just find a text editing program, such as Notepad, enter some text, select it, and then press Ctrl+C, which is the familiar copy action. Now switch to sproc, create a new cell set, enter equals clipboard in cell A1, and then execute to see the value of cell A1. The text just copied in Notepad is now here. The clipboard function can take out the text copied to the system clipboard. Then enter greater than sign, clipboard hello sproc in A2. After execution, switch back to Notepad and press Ctrl+V to paste. What do you see? The clipboard function with the parameter will copy the string used as a parameter to the system clipboard, and then it can be pasted in other programs. Now let's use this clipboard function to help Excel do something. Suppose a column in Excel, such as column A, has some names. For example, the first few rows are like this. Now we want to know how many times the letter E is used in these names. It's not easy for Excel to calculate this. Let's use SPL to cooperate. 1. Select this column in Excel, press Ctrl+C and copy it to the clipboard. 2. Switch to sproc and write the code. Execute it. A5 is the result we want. Let's look at each cell value in the script after the code is executed. A1 is like this. It takes out the content just copied in Excel from the clipboard. It seems to squeeze the text in the column of Excel together. Look at A2. This is a sequence. Each member is exactly every row of text in the Excel column. How does this happen? In fact, what we copied from Excel is a large string composed of these texts, separated by return between the two rows. The return character is a non-displayable character which cannot be seen in sproc, so it looks like squeezing the text of these rows together. A1.split\n means that the return character is used as the separator to split the large string into a sequence, so it returns to the case where each member exactly corresponds to each row in Excel. The \n here is the return character. The backslash in the string constant is called the escape character. Its function is to help us write some characters that are inconvenient to write. For example, return is represented by \n and tab is represented by \t. These are non-displayable characters, but they also have codes and are two characters. \n is only one character in the string, although it is written in quotation marks as two characters \n. \t is also similar. Because \/ is regarded as an escape character, if we really want to have a \/ in the string constant, it will be escaped. It will be written twice, that is, the actual content of a \b is a \b, and the length is 3. In addition, double quotation marks are used as the delimiter of a string, but it is still possible that a string contains double quotation marks. In this case, it should also be written with an escape character. The actual content of double quotation mark a \, double quotation mark b double quotation mark is a double quotation mark b with a length of 3. The following statements are simple. A3 is a loop function. Its inner tilde.split will split the string of each member into a sequence of single characters, so A3 is a two-layer sequence. We have encountered the conjunction function when we talked about recursion. Its function is to concatenate the member sequences of a multilayer sequence and return the result of sequence concatenation operation among these members. Therefore, A3.conjunction in A4 will get a one-layer sequence. The lower function turns the character into lowercase. Now it can be compared with the string E, and then count it. It is written in this way to disassemble the steps and facilitate the interpretation of the code. In fact, these operations can be written continuously. S.split at nx is S.split \n.tilde.split x because it is common to split by return first and then split again. SPL adds the @n option to the split function. Let's take another example. A batch of email addresses are stored in a column in Excel. As we know, the email addresses are X at Y format. We hope to sort these email addresses so that the mailboxes of the same enterprise can be arranged together, that is, we hope to arrange them in the order of Y first and then X. For example, abc@google.com and xyz@google.com should be arranged together instead of putting abc@google.com and abc@apple.com together, but the latter situation will occur if they are sorted directly in Excel. We still use the clipboard. First copy this column of data in Excel, and then switch to Spreadsheet to write code. Execute the code, then switch back to Excel and paste it in that column with Ctrl V. It has been arranged as we want. We've understood A1. The split at n in A2 first split the string into a sequence of strings according to the return character, and then split each member with the separator at. There is and will only be one at in an email address, so each member string will be split into a sequence of two members, which are the parts before and after at, respectively. Then, when sorting with the sort function, write the sequence members in reverse. In this way, according to the sequence comparison rules, the later part of at will be compared first and then the front part of at, that is, the order we want. Concat in A4 is the opposite function of split. Split is responsible for splitting, and concat is responsible for concatenating. The at n option indicates doing concat for the two-layer sequence. Each member is restored to the original email address string and assembled into a large string separated by return, but now the order is reasonable. Then use the clipboard function to copy it to the clipboard. In Excel, just paste it. A4 can also be directly written as A3.sort_2-1. The sort function also supports multi-parameter form, which means comparing the previous parameter first and then the following parameter. For a sequence with single values, multi-parameter sort is of little significance, but it will be more convenient for a two-layer sequence. After learning structured data in the future, multi-parameter sort will be more common. Now we are dealing with a single column data in Excel. How about multiple columns? Of course, there's no problem. For example, in Excel, we want to sort the data of each row from small to large. Excel usually sorts by row, and it is difficult to sort in the column direction. It is easy to implement with SPL. Select and copy this piece in Excel, and then switch to Sproc to execute such code. Then paste it back. The piece of data copied from Excel is a large string after being received by the clipboard function. Each row is separated by return, that is, \n, and the columns in each row are separated by tab, that is, \t. So A1.split at n\t in A2 can split this large string into a two-layer sequence, and its inner member is just the data of each cell in Excel. Then sort each row in A3, concatenate it back into such a \n and \t separated string in A4, and paste it into Excel. Look carefully at the results in Excel. It seems that there is something wrong. It ranks 42 in front of 5. Is the size wrong? In fact, it's not wrong, because the result that is split by the split function is still a string, and as a string, 42 is smaller than 5. So how can we compare by value? We need to change A3 to equals A2.tilde.sort number tilde. Corresponding to string, number can convert a string parameter into numeric type, and then it can be compared and sorted according to numerical rules. Look now, there's no problem. Under the previous operating system, there was a command called grep, which can find the file containing a string and the line number in many text files. This is a very useful command, which was cancelled by Windows. Let's implement it by ourselves now. Assuming that the string to be found is in A1, let's specify all text files under the path. We're going to learn a few new functions. The directory function in B1 will return all .text file names under the specified path. It is better to use the absolute path, otherwise the file may not be found because the startup path of sproc is uncertain. These file names will be returned as a string sequence. At P indicating that the returned file name is also a full path. A2 loops this sequence, B2 reads out each file, and the file function generates a file object with the file name. Read at n function reads the text file into a sequence of strings, one member per line. The filename function takes out the part of the path in the full path file name. B3 to D3 is easy to understand. Loops through each line of text. If A1 is found, output the file name, line number, and the content of this line. Here we assume that the files are small and can be read in at one time. If the file is large, we need to use the cursor technology mentioned later. Counting the number of words in a batch of articles is also a common exercise. After learning to read files, we can also practice. The read function without options will read the whole text file into a large string, and the words function will disassemble the words in the large string to form a sequence. Then, just count the length and add it up. One line is enough. Let's do another task that may be useful in daily work: merge a batch of Excel files into a large one. We may often collect Excel files of various periods or departments. The Excel format is the same. These files need to be combined into a complete file to facilitate further statistics. But manual copy and paste is very troublesome. If there are dozens or hundreds of files, it will be very tiresome. This kind of thing is just for the program to do. Let's assume that the Excel to be merged is row type. The first row is the title, and then each row is data, such as. This is a very common Excel file format. Add a requirement to spell the original Excel file name into the last column of the merged Excel, so as to distinguish which file the data comes from. File name at N in B3 will disassemble the part of the file name with the extension removed, and it can also be done by splitting a string. XLS importer W in B2 will read an Excel file into a two-layer sequence. Each row of Excel corresponds to one member, and each column in each row corresponds to the member of its member. B4 removes the title of the first row and spells the file name to the end of each row. B5 combines these data, while B6 needs to keep one title and spell one more column. Finally, XLS exporter W in A7 write the summarized two-layer sequence into a new Excel file. It is better to use the absolute path when exporting the file. XLS import without a W option can actually read an Excel file into more convenient data type, and the code to complete this task will be simpler, but it will be introduced after we talk about structured data. With the in-depth study, we will gradually enter the phase of handling practical tasks. Processing file data is a very common task. In the examples of this section, we all use absolute paths to locate files. Here is a brief introduction to the file search rules of sproc when using relative paths. If the main path is set in the environment, sproc will start from this main path. If the main path is empty, search from the path where the currently used script file is located. The current script may have just been created and have not been saved. In this case, there is no path, so it cannot determine where to find it, and it is likely that it will not be found. Therefore, either set the main path, or the current script is saved and has the path. The searching path that was set at the same time as the main path is used to search the called script, and it has nothing to do with the data file. Placing the data file in the searching path will not enable it to be found automatically. Do some experiments by yourself, and it's easy to figure it out. When we give examples later, we will use a simple relative path. Please adjust the appropriate system configuration and the path in the code according to the above introduction. Section 3. Date and time. Time-related processing and calculation are also common. SPL has three data types: date, time, and date time. Date data has only date information but no time information. Time data has only time information and no corresponding date information. Date time has both date and time, which is equivalent to a certain moment. It is necessary to provide a time type without date information. Some events that occur on an uncertain date do not have date information, and it is more appropriate to use a time type. An extra date may cause confusion. For example, calculate the interval between 8 o'clock and 9 o'clock. If there must be a date information, we have to pay attention to whether it is 8 o'clock and 9 o'clock of the same day, which is easy to be neglected. But with a more precise date time type, why should there be an imprecise date type? This is similar to integer and floating point number, because for many events, we only care about the date of occurrence and no longer care about the time. If only date time type is used, the amount of storage and calculation will become larger. Moreover, when comparing whether the two dates are equal, we should also pay attention to whether the attached time information is also equal, and errors are likely to occur. Not all programming languages provide these three data types, and most databases have only datetime and no date. The most basic operation related to date and time is the splitting and combination of components. These functions are very simple. Just look at the examples, and there is no need to explain them in detail. SPL also supports putting the month and year together as a component, that is, a 6-digit number. Sometimes you will find this kind of processing very convenient. The conversion between datetime and string is troublesome, and there are many kinds of formats. For example, 2020-12-20 may also be written as 2020/12/20, 12/20/2020, 20-12-2020. Europeans and Americans may also use the format December/20/2020 or 20-December-2020. The formats of time are relatively less, but it may also be written as 10:03:05 p.m. or 22:3:5. Therefore, a program language that can handle date and time usually provides the ability of format parsing and conversion. The writing method of these format strings can be found in the function help. It is almost a common rule all over the world, and we will not explain in detail here. You only need to know this usage. It should be emphasized that since the starting letter of month and minute are both M, it is necessary to distinguish them by uppercase and lowercase. You can observe B8. By the way, numerical values also have format problems which are not explained in detail. Just try it yourself. As we said earlier, there are only numbers in the computer, and other data types are actually numbers by some kind of coding. For example, the string in SPL is encoded by Unicode, so how is the date and time encoded? The internal codes of date and time data types are long integers. Let's observe their rules. First observe C2, two dates with a difference of 1 day. After converting to long integer, the difference is 86,400,000. What is this number? Readers who often do date calculation will sensitively find that 86,400 is equal to 24 times 60 times 60, and it is exactly 1,000 times the number of seconds of a day. Then look at C4. The difference between two dates with a difference of 1 second is 1,000 after converting to a long integer. This confirms our idea that the long integer corresponding to date and time is the number of milliseconds from a certain moment. Then, from which moment? We can't figure it out by observing A1, B1, A4 and B4 directly. We can simply reverse it and observe A5 and B5. It turns out that the date is counted from January 1st, 1970. This is an agreement of the International Computer Standards Organization. Dates earlier than 1970 should be expressed as negative numbers. Interestingly, several days in history are not exactly 86,400 seconds, and the long integer value corresponding to a date is not always the number of days from January 1st, 1970 multiplied by 86,400,000. Interested readers can program to find out which days, and then search the internet to see why these dates are not 86,400 seconds. With the skills we have learned till now, readers should be able to do this. Let's look at the time. The result of B5 is strange. I calculate it here as 8 o'clock. Why not start from 0 o'clock? Because I am writing this book in Beijing, China. The time zone of Beijing is East Zone 8, and 8 o'clock Beijing time is exactly midnight GMT. The time is counted from midnight, but it is Greenwich Mean Time, not the local time zone. If you happen to be in the UK now, the calculated B5 will be 0. There are so many interesting things about date and time. Let's continue to learn about date and time operations. The most common requirement is to calculate the gap between two moments and the time after a period of time from a certain moment. For example, if we want to see how effective the optimization method used in the calculation of Narcissus number is, we need to calculate the execution time of this program. Here we need to use the code that generates the result sequence, because the output method will involve screen display. In fact, this action is very complex, and it may take longer than completing these calculations, and it is not the test of calculation time. Moreover, we repeated this action 1,000 times, because the CPU of modern computers is so fast that we can't see the difference by only executing it once. The now function of A1 will return the time when this statement is executed, that is, record the start time of the program in A1. At A7, use now function to get the time when the program ends, and then use interval at ms to calculate the gap between the two moments and write the two parameters in chronological order, so as to get the execution time of the program. The now function returns the datetime type, which can be accurate to milliseconds. The at ms option of interval function means that the calculated time gap is accurate to milliseconds. Because the program executes very fast, even if it is repeated 1000 times, if it is not accurate to milliseconds, we still cannot see the gap. Now do the same transformation to the optimized code and execute it. Comparing these two time gaps, we can know whether optimization works. On my computer, the optimized code is about 25% faster, which is pretty obvious. The interval function has various options and can return the time gap of different accuracy. In daily work, the most common task is to calculate the number of days between two dates, which is also the default return value of the interval function when the option is not used. Moreover, because it is too common, SPL simplifies this calculation to be expressed directly by subtraction, that is, interval D1, D2 equals D2 minus D1. Someone borrowed $25,000 on December 4, 2018, with a daily interest of 0.013%. If he pays it back today, how much interest should he pay? The results of A1 and A2 are the same. The now function contains date information, and can be used as today. Let's make the case a little more complicated. If the interest is added to the principal at the end of each year and the following interest is calculated on this basis, how much should be paid in total when it is returned today? In other words, on January 1st of each year, the interest at that time shall be calculated and added to the principal, and the following interest shall be calculated on this basis. We use a clumsy way to calculate, looping day by day from the loan date to today. The current interest is stored in D1. The initial value is 0. For every day of the loop, the interest will be increased by 1 day. If the current date is January 1st, add the current interest to the principal and then clear the interest. At the end of the loop, add the principal and interest at that time. It should be noted that in cell B3, the elapsed d(n) function returns the date n days after a date d. With this action, the loop can run normally. Like interval, elapse has many options to control accuracy. Moreover, when the accuracy is days, it can be expressed directly by addition. That is, cell B3 can be simply written as greater than sign A1 equals A1 plus 1, or even greater than sign A1 plus equals 1. The percentage constant can be directly expressed by percentage sign in a cell, but not in the expression. Percentage sign will be regarded as the operator of remainder.